In this video, we discuss finding the volume between two surfaces. It's analogous to finding the area between two curves. So remember, you studied this back in Calculus 1 or Calculus 2. Let's say you wanted to find the area between y equals f of x and y equals g of x on the interval from x equals a to x equals b. Well, there are a couple of ways we were able to derive the integral representing that area. But one way that we did it was we took this interval from a to b and we subdivided it. We created n subdivisions of equal width, and then on each of those subdivisions we chose a particular x value. Let's say we called that x sub I. And then we evaluated the bottom function at x sub I and the top function at x sub I, and we created a little rectangle there. And we did that for all of the x sub I. If we've got n subdivisions, we created n little rectangles like this. And we said that if we want the area between the two curves, well, it's pretty simple. If we can find the area of one of these, then we can add up the area of all of the rectangles, and then we can take the limit as the number of rectangles goes to infinity, or alternatively as the width of that rectangle goes to 0, which is equivalent if all of these intervals have the same width, and then we find the area between the two curves. So it all came down to being able to find the area of this one rectangle. And of course we know if this is the ith rectangle, I'll call the area of the ith rectangle a sub I. We know the area of a rectangle is just length times width. The width of this rectangle is a tiny distance in the x direction, so we call that delta x. And then this is just the difference between the two y values. So this is the top y value minus the bottom y value, or f of x sub I minus g of x sub I. So when I'm trying to find the area, I do length times width, and I get this. And then we took the sum of these as I goes from 1 to n. Then we took the limit of that sum as n goes to infinity, and we derived an integral. And that integral looked something like this. Well, it looked exactly like this. We said the area between the two curves is the integral from a to b of f of x minus g of x. And in the limit, that delta x became infinitely small, so small it was an infinitesimal, that we labeled dx. So that was the area between two curves. Now, in Calculus 3, we sometimes find the volume between two surfaces, and the idea is the same. You've got some region R. I'm not going to sketch it down here, but there's a region R in the xy plane, and in that region R, you'd like to find the volume between f of xy and g of xy. Well, the way we did that was we would take the region R and we would subdivide it into n subdivisions in the x direction and m subdivisions in the y direction, and that would create a bunch of little rectangles in the xy plane with an area delta x delta y. Now above each of those rectangles we would create a little rectangular prism, and the way we would find the height of that rectangular prism is we would evaluate this function f of xy and this function g of xy at a particular xy inside that rectangle. And if we're in the ith subdivision in the x direction and the jth subdivision in the y direction, we would call the x value here x sub I, and the y value, where we're evaluating these points, y sub j. So the volume of that ith jth rectangular prism, that's the prism in the ith subinterval in the x direction and the jth subinterval in the y direction, that's just length times width times height. Well, length and width are delta x and delta y, And the height of this guy is just the top z value minus the bottom z value, just like the length of this one was the top y value minus the bottom y value. So the height of this is f of x sub I, y sub j, minus g of x sub I, y sub j. So we get the volume is length times width times height, which is the difference between the two z values, times delta x times delta y. And if I want the total volume between the surfaces over the region R, I would take the sum of this as I goes from 1 to n to get all the subdivisions in the x direction, and then take the sum of that as j goes from 1 to m to get all the subdivisions in the y direction. That double sum became a double integral, and we said the volume is the double integral over the region R of f of xy minus g of xy, and in the limit delta x and delta y become dx and dy, and of course you can change the order because multiplication is commutative. Let's just call that dA. Now this is our formula for this section. This label f of x, y, and g of x, y, these two labels really don't matter. What matters is that you realize that f of x, y in this formula represents the top function and g of x, y is the bottom function. The top function is associated with larger z values, and the bottom function is associated with smaller z values. Now, in practice, if I want to use this integral to find the volume between two surfaces, all I have to do is identify the top function and the bottom function. And notice we've got z equals f of xy and z equals g of xy. So I need to figure out what z is on top and what z is on bottom. Put those here. And then we need a description for the region R. We'll describe the region R using the techniques that we talked about in earlier videos for finding the area of a region R using a double integral. So all of that we studied with area from before is important because that will allow us to describe the region that we're integrating over in this section. Okay, so that's the plan. Now, in practice, this usually isn't too bad if the region R is given to us. Sometimes they give us a picture, sometimes they give us equations, sometimes they tell us the region R is bounded by some functions. In all of those cases, it's really not too bad to find R. You just draw it, and then you can use your picture to figure out how y goes from a function to a function and x goes from a constant to a constant, or the other way around where x is going from a function to a function and y is going from a constant to a constant. So if that's given, it's not too bad. Now, sometimes this is more challenging though. If the region R is not given to you, they just say find the volume between the two surfaces. And what that implies is that those surfaces meet somewhere. And there's an implied boundary just given by the equations of the surfaces themselves. You've done something like this before when you're looking for the area between two curves back in Calculus 1 or Calculus 2 when you first studied this idea. So this integral from Calc 1 and Calc 2 isn't too bad if somebody gives you a and b, but sometimes they didn't give you a and b. They said something like this. Here's f of x, and here's g of x. Find the area between the two curves. And you had to identify which function is the top function and the bottom function, and where is x equals a and where is x equals b. So this time, with the labels that I've used, f of x isn't the top function, f of x is on the bottom, and g of x is on top. So don't let the labels trick you. It's not important that f is first and then we have g. What's important is that we have the top function minus the bottom function. And if they don't give you a and b, in order to find a and b, we had to set the two y values equal to each other and solve for a and b. Something similar will happen here with volume. if they don't give us the region R in some form, if they just say find the volume between the two surfaces, you'll have to set the z values equal to each other and solve for the boundary of R, as we'll see in the first example. Well, there's only going to be one example in this video. So here it is. Let's say someone asks you to find the volume between the elliptic paraboloid z equals 8 minus x squared minus y squared, and the plane given by 2y plus z equals 8. Well, the first thing I want to do in any problem where I'm asked to find the volume between two surfaces is I always want to graph the surfaces just to get a better sense of what's going on. Graphing the surfaces will also help me identify the top function and the bottom function here. Now, I'm never going to ask you to graph surfaces that we haven't already discussed. So it'll be, whenever I ask you to graph a surface, it will be one of your quadric surfaces that we studied earlier this semester. It might be a sphere, it might be a plane, or it might be a cylinder. So all of those are fair game, but I wouldn't ask you to graph anything that was too complicated. Those are the only things that I would expect you to know how to graph. Okay, but this is an elliptic paraboloid, so we know how to graph that. Now, they told us it was an elliptic paraboloid, so that helps. But even if they had not told us that this function represented an elliptic paraboloid, we could figure it out. Because we've got a z to the first, you have an x squared and a y squared term, and notice that they're both negative. Now, if you have a z to the first and the other two variables are squared, and they both have the same sign out front, that tells you you have an elliptic paraboloid. Now, if this was a plus sign and that was a plus sign, if they were both positive, we'd have an elliptic paraboloid facing up. But that's not what we have. This is a transformation of the elliptic paraboloid z equals x squared plus y squared. We took that elliptic paraboloid and we multiplied it by -1. So instead of facing up, now the elliptic paraboloid is facing down. And then we added 8 to it, and that shifted the whole graph up 8 units, just like adding 8 to a function y equals f of x shifts the whole graph up 8 units. So it's the same thing, it's just a 3D version of transformations of functions. When x and y are both 0, z equals 8. And so we've got an elliptic paraboloid facing down. Now this goes on forever. The range of that is -∞ to 8. So we're good there. I wanted to see where it intersected in the xy plane because that's just a nice visual marker of what's going on. To figure out what that boundary is, to figure out where our elliptic paraboloid crosses the x and y axes in the xy plane, you can set z equal to 0. Because in the xy plane, that's the plane z equals 0, and then z equals 1 is 1 unit above that, z equals 2 is 1 unit above that, and z equals 8 is that plane parallel to the xy plane that's 8 units above the xy plane. So down here z equals 0. So let's look at this. When z equals 0, we have 0 equals 8 minus x squared minus y squared. And if we add x squared plus y squared to both sides, we get x squared plus y squared equals 8. Now, just using pattern matching, this represents a circle. I'm not subtracting anything from the x or the y. From our study of circles, we know that that means the center of this circle is 0, 0. If you don't remember that, you might want to look up graphs and equations of circles, check that out. And on the right-hand side, we've got r squared in general. That's the radius squared. So r squared is 8. So that means r is the square root of 8, or 2 root 2. And 2 root 2 is approximately, I believe this is 1.4, so that's approximately 2.8. So you want to keep that in mind. So it's a circle centered at the origin with radius 2 times the square root of 2, which is about 2.8. So that's 2 root 2. That's 2 root 2. That's negative 2 root 2. And that's negative 2 root 2. And again, remember that that's 2.8. Okay, so I've graphed my first surface. Now we're also asked to graph this plane, or we need to graph this plane so that we can identify the top and bottom function. And notice, even if they didn't give this to us, we would know that this is a plane because y is raised to the first power and z is raised to the first power. Anytime all the variables are raised to the first power and we are in three-dimensional space, this will represent a plane. So this is a plane, but notice that the x is missing. The fact that the x is missing means that this is also a cylinder. So what that tells us is that this is really just the line. I can think of this as the line 2y plus z equals 8 back here in the yz plane. But then we're going to have that same line over and over again. We'll see that line when x equals 0 in the yz plane. We'll see the same line at x equals 1. And we'll see the same line when x equals 2 and x equals negative 100, x equals positive 100. We're going to see that line all the time. So this is a plane that is a cylinder. Its rulings are parallel to the x-axis because the x is missing. So it's like once we draw that line, we can imagine that line continuing, coming out of the page parallel to the x-axis. Okay, so now we want to graph this plane. The easiest way to graph this plane is to graph the line back in the yz plane. And the easiest way to graph the line is to just find the intercepts. So I would set one variable equal to 0 and solve for the other one, and then you can figure out where your plane crosses the y-axis and the z-axis. So let's look at this. When y equals 0, we just end up with z equals 8. So we're right there. And when z equals 0, this is on the plane. When z equals 0, we get 2y equals 8, which of course means that y equals 4. So our plane, or at least the trace of that plane in the yz plane over here, passes through the z-axis at z equals 8, and it passes through the y-axis at y equals 4. That's a little bit, that's over here somewhere. This is not to scale. So our line passes through here and it passes through here. Now if we put those two pieces together, you can kind of see it. I tried to do a good job with my graph. It's not perfect, but we do the best we can, right? So that's the line that you would see in the yz plane, but remember this is a plane that's parallel to the x-axis. So we're going to see exactly the same line coming out at us. So our plane kind of looks like this. Okay. And notice that like this line is going below our elliptic paraboloid. So what we would see is that plane is going to intersect the elliptic paraboloid. It's going to slice a little bit off of the top. And when it slices a little bit off of the top, it's a little bit hard to draw. We're going to see something like that. We want the volume of that solid region in between the plane, which is on the bottom, and the elliptic paraboloid, which is on the top. So we wanted to graph the surfaces so we could identify the top function and bottom function. Now we have. The top function is the elliptic paraboloid and the plane is below it. The plane is cutting into our elliptic paraboloid. So that's the bottom function. Now we've identified the top function and bottom function. We also need to find the region R. So let me write all of that down, and then we'll find the region R. So we graph the surfaces, then we identify the top function and bottom function. And we can see from our picture that the elliptic paraboloid is the top function. Oops. And notice the way that these were written over here. We had z equals a function of x and y, and z equals a different function of x and y. So for the top function, we have z equals 8 minus x squared minus y squared. That's the equation of the elliptic paraboloid. So that will go in here. And then the bottom function is the plane, but the way the plane is written right now, we don't have z by itself, so we have to solve this for z. We get z equals 8 minus 2y when we subtract 2y from both sides. Okay, so we've graphed the surfaces, we identified the top function and the bottom function. So we're there. Now we need to find the region R. Now the easiest way to find the region R is to sketch it and then use our sketch to find appropriate bounds for x and y. Now let's think about this before we try to find it algebraically. The region R is the projection of this solid region onto the xy plane. So you want to imagine like there's a sun over here. Or maybe it's directly above this, and the sun is casting a shadow onto the xy plane, or this part is casting a shadow. We want to know, where's the shadow going to be cast? I think what we'll see when we slice this is we'll see something that looks like this. Maybe it's an ellipse, maybe it's a circle. Down here in the xy plane, we're going to see some shape that looks like that from where our plane sliced off top of that elliptic paraboloid. That's the region R. Now in order to find the region R, we need to find the boundary of that region. And the boundary of that region is found in a very similar way to the way we found the points of intersection A and B back in Calculus 1. So when we're trying to find the area between two curves, if they don't give you A and B, well then what did we have to do? We said, well, at A and B, the y values are equal to each other. So if I call this one y1 and I call this one y2, we would just set y1 equal to y2 and then solve for x. And you would usually get two x values, and the one on the left was your A and the one on the right was your B. We're going to do something similar here, except we're not going to solve for x and y. We're going to end up with an equation. We'll set the z values on the plane equal to the z values on the elliptic paraboloid, and that's going to tell us the equation of a curve where those z values are the same. That's giving us the boundary of the region R, and then we can see just from the picture that the region R is the interior of that region. So that's the plan. We've graphed the surfaces, identified the top function and bottom function, and now to find the region R, if it's not given to us, we'll set the z values equal to each other and solve for the boundary of R. Okay, so we'll set the z value on the elliptic paraboloid equal to the z value on the plane. And on the elliptic paraboloid, z equals 8 minus x squared minus y squared. On the plane, z equals 8 minus 2y. And I'll set one side equal to 0. So we subtract 8 from both sides. We'll add x squared and y squared to both sides. By design, that's 0. And then on the right-hand side, we've got x squared plus y squared minus 2y. Now, a lot of my students would just ignore the y, and they'd say, hey, that's a circle, but they would be wrong. Because let's look at this picture over here. It looks like it could be a circle, or an ellipse or something like that, but it's not centered at the origin because the plane and the elliptic paraboloid intersect here on the z-axis. That entire solid is over here in this region where y is positive. It doesn't exist over here where y is negative. So yeah, that y matters. This is a circle, but because we've got a y squared and a y term, it's not written in standard form. We need to complete the square to write this in standard form, and then it'll be easier to graph it. So remember how we do that. If you have multiple x terms, you would group those together. We don't have multiple x terms this time, so we'll leave the x squared alone. We do have multiple y terms, so we'll group those together, and then we'll complete the square. Excuse me. Now, if there was a number in front of the y, we would factor that out from this term and this term. Since there's an implied 1 there, we're good to go. We're ready to complete the square. When there's a coefficient of 1 in front of the y squared, b is the number in front of the y. You take half of that, and then you square it. Of course, negative 1 squared is negative 1 times negative 1, which is positive 1. That's what you add to complete the square. And if you are adding that to the right-hand side, that's legal, as long as you also add that to the left-hand side. So on the left-hand side, simplify that, we get 1, and we have an x squared over here. And then this factors as a perfect square. Now, first times first has to be y squared, so we'll have a y here. So this will be y plus or minus a constant squared. To figure out what that constant is, take the square root of this number. Square root of 1 is 1. And since that's a minus, this will be a minus. Okay, now we're pattern matching. We're looking at this and we're comparing it to this pattern for the equation of a circle in standard form. X naught, y naught is the center of the circle in general. And the radius of the circle is r, where this side, the constant side, is r squared. So that's just in general. Well, through pattern matching, I can see that the center of this circle, let's see, I'm not subtracting anything from the x, so the x coordinate of my center is 0. And I am subtracting a 1 from the y coordinate, so I get a 1 there. Radius squared is 1, so if I take the square root of both sides, and of course the radius is positive, we get r equals 1. So this is a circle centered at x equals 0, y equals 1, with a radius of 1. So let's draw it. So the center is 0, 1, x equals 0, y equals 1, and the radius is 1. So from the center, we want to add 1 and subtract 1. So you want to go up 1 and down 1 to find points on your circle. And you want to go left 1 and right 1. Okay, now that's not R, but that's the boundary of R. And that's actually very consistent with this picture over here. I see a circle, or maybe an ellipse, but it turned out to be a circle. It's off center. It's not centered at 0, 0, 0. It's centered at a point on the y-axis, which is what we see. And it lies over here where y is positive, not where y is negative. So it's the exact same thing, it's just oriented slightly differently because our y-axis is this way and our x-axis is this way. And now we've got it sort of turned. Our x-axis is this way and our y-axis is this way. So this is the region R. Now remember what we're trying to do. We're trying to find the volume of the surface, or excuse me, the volume between these two surfaces. We identified the top function and bottom function, and now we need to describe R. We need bounds for R. And we know R is the interior of this. Now in order to find bounds for R, we need to draw rectangles. We can either let x go from a constant or a function to a function, and let y go from a constant to a constant, or we can let y go from a function to a function and let x go from a constant to a constant. I think it's easier in this case because we've got the x squared already by itself. I'm not adding or subtracting anything from the x, whereas I am subtracting a 1 from the y. I think it's easier to solve for x as a function of y as opposed to solving for y as a function of x. So I'm going to let x go from a function to a function. So I'm drawing my rectangles this way. So x is going from a function on the left to a function on the right, and y is going from a constant to a constant. So after you have solved for the boundary of R and you've sketched R, you need to describe R with appropriate boundaries. Or I said appropriate boundaries, appropriate bounds. Okay. So we can let x go from a function of y to a function of y and let y go from a constant to a constant, or the other way around. I have decided to do it in that order. I want x to go from a function to a function and y will go from a constant to a constant. So let's do the constant bounds first because it's easiest. Y starts at 0 and ends at 2. So our bounds for y are 0 and 2. To find the bounds for x, I'm going to take this equation and solve it for x. Or alternatively, you could take this equation right here and solve it for x. Let's take this one before we've added the 1 to it, before we completed the square. So I'm solving for x now, and I have 0 equals x squared plus y squared minus 2y. And I will add 2y to both sides, and then subtract y squared from both sides, and then switch sides. So we'll get this after simplification. And I'm trying to get x by itself, so we'll take the square root of both sides, and don't forget they're plus or minus. So we get x equals plus or minus the square root of 2y minus y squared. And that is giving us the two bounds that we need. Now at first students are like, oh no, that looks really bad. It is a little bit bad, but it's not too terrible because the positive square root is actually the bound on the right, and the negative square root is the other side. Where on this side, the positive square root, the x is a positive square root, because x is positive or possibly 0 over here. On this side, we have the negative square root. Okay, so x goes from the negative square root to the positive square root. And that's it. Those are our bounds for x and y. Now that we have our bounds for x and y and our top function and our bottom function, we're ready to set up the integral representing the volume between the two surfaces. And then we can evaluate that integral. You'll see in this section in this chapter, what we'll keep doing is we'll keep drawing pictures and keep drawing projections of surfaces onto the xy plane, and then using the picture of the projection to find the appropriate bounds. So we're setting up the volume, or the integral representing the volume between the two surfaces. Okay, we're right here. We have volume equals the double integral over r of the top function minus the bottom function. And our top function was the elliptic paraboloid. Remember, it's this picture right here. So we've got 8 minus x squared minus y squared. And the bottom function was the plane. It's 8 minus 2y. And then we'll simplify. You don't really need the parentheses on the first polynomial function in x and y. You can distribute the negative here. And of course the 8's reduce. Now I have negative x squared minus y squared plus 2y. But notice I've got a 2y minus y squared under this radical. In order to make everything simpler later, I think I want to group that 2y minus y squared together, because later I'm going to replace all of my x's with functions that look like this. So seeing another function that looks like that here might make our algebra simpler later. So I will group these together and call that 2y minus y squared. Okay, so that's our integrand. So we simplified the integrand. Now we're going to substitute the bounds. Excuse me. We have the integral from 0 to 2 of the integral from the negative square root of 2y minus y squared to the positive square root of 2y minus y squared. We're integrating negative x squared plus the quantity 2y minus y squared. And these bounds are our bounds for x. So we integrate with respect to x first, and then we integrate with respect to y. And then remember how this works. Whenever you're evaluating an iterated integral, you do the innermost integral first. Use the fundamental theorem of calculus to simplify this, and then you do the outermost integral. Okay, so now we're getting ready to evaluate the integral. And one thing that I'd like to do to simplify this calculation a little bit is just to remember that a square root of a number is actually that number to the 1/2 power, because there's an implied 2 there and an implied 1 there. And using our properties of rational exponents, this is a to the 1 over 2. The 2 goes in the denominator. I'm going to use that to simplify these in a little bit. So we're integrating with respect to x. The 0 to 2 on the outside, I'm not really doing anything with it. The antiderivative of negative x squared with respect to x is negative x cubed over 3, according to the power rule. And then this is constant with respect to x. The antiderivative of a constant is a constant times our variable. So we get the constant, 2y minus y squared, and we multiply by the variable x. So we are first anti-differentiating. And then we evaluate this from the lower bound for x to the upper bound for x. I'm going to use this property now to rewrite my lower bound as a negative 1 times the quantity 2y minus y squared to the 1/2. And my upper bound is the quantity 2y minus y squared to the a 1/2 as well. But that's a positive expression to the 1/2, and that's a negative expression to the 1/2. So by the fundamental theorem, we're going to evaluate this at the upper bound and lower bound and subtract. So that's just the fundamental theorem of calculus. And then we'll simplify and integrate the result with respect to y. When I substitute this in for x here, this is going to get long. So I'll have a negative 1/3, and then I've got x cubed, and over here I've got 2y minus y squared times x. I'm replacing x with 2y minus y squared to the 1/2. And over here, I'm replacing x with the same thing, 2y minus y squared to the 1/2. That is this expression evaluated at the upper bound. So that's our f of b. Now I have to take all of that, oh my goodness, and subtract all of this evaluated at the lower bound. There's not going to be enough space. I'll do the best I can. Maybe I'll do that. This is 2y minus y squared, and then we'll put in our x over here. Can't even see it, it's off the camera. There's a dy over here. Now you're replacing x with this now, and that has a negative out front. So I've got a negative 2y minus y squared to the 1/2 right there. And this is a negative quantity of 2y minus y squared to the 1/2 right there. Okay. Now we have to simplify this, and we'll integrate the result with respect to y. It looks terrible, but actually simplifies really nicely. I got interrupted while I was making this video earlier, so I've done this one before. That's how I know it simplifies nicely. Okay, so I've got the integral from 0 to 2 of this. Now to simplify this, notice you've got something raised to a power raised to a power. We're going to use some of our exponent properties to simplify. Remember, if you've got something raised to a power, all you have to do is multiply the exponents. That's x to the n times m. So here I have a negative 1/3 times the quantity 2y minus y squared, and that's to the 1/2 cubed. So I just multiply the 1/2 and the 3, I get 3/2. That's that right there. Now here, there's an implied 1 there, and I actually have something very similar. It's not that exponent property, it's a different exponent property. You've got x to a power, or something to a power, times something else to a power. The bases are the same. We've got the same base here. We have a 2y minus y squared and 2y minus y squared. Well, if you have something like this, you just add the exponents. So this will become a 2y minus y squared to the 1 plus 1/2, and 1 plus 1/2 is 3/2. Okay, now over here I've got something very similar, but notice I have a negative 1 in front of this quantity because of that lower bound being the negative square root from earlier. The negative square root was over here. So there's a negative there. Now the property I need for this, if I have something times something else cubed, is this. If you have something, a product cubed, you can apply that power to each factor separately. So I can apply that third power to the negative 1, so it's going to give me a negative 1, times all of that cubed, which is going to give me 2y minus y squared to the 3/2, because we're going to multiply the exponents. Excuse me. I knew I was about to sneeze. If you're wondering why there's suddenly silence, that's why. Okay, so we'll have this to the 3/2 times a -1. That -1 times that -1/3 is going to make that a positive 1/3, but then we distribute this negative to it. So we have a positive 1/3 times that -1 is going to be a -1/3 times 2y minus y squared to the 3/2. Well, I actually already have one of those. So when I distribute that negative here, I'm going to have two of them. So when we collect like terms, we'll have -2/3 of these guys. Now let's see what happens over here. Something very similar happens. This is a 2y minus y squared to the first times a -1 times a 2y minus y squared to the 1/2. Well, just like we had over here, I've got the same base twice, so I add the exponents. I have the same base twice, so I'll add the exponents. I'll have a 2y minus y squared to the 3/2 times a -1. But this negative out here has to distribute to both terms. So I've got a -1 times that -1, that's going to make it a positive 1. So I end up with a positive 2y minus y squared to the 3/2. And I already have one of those. So now I've got two of those. And that's it. We're integrating with respect to y. So it's already much, much simpler. And this is even cooler. Look at that. They're pretty much the same thing. I've got a constant times this to the 3/2 plus a different constant times that to the 3/2. So this can be simplified even further. We'll just do the 2 minus the 2/3. That's 6/3, because 6/3 is the same as 2. 6/3 minus 2/3 is 4/3. So you can factor that out. And now you have the integral from 0 to 2 of 2y minus y squared to the 3/2 power. Now, evaluating this integral, that's our job next. We used the fundamental theorem of calculus to evaluate this guy, and then we did a bunch of algebra to simplify. And now we're here. And our job is to anti-differentiate this function with respect to y. Okay. Now in order to do that, I say to myself, do I have a basic rule for that? No, I don't. It does kind of look like a u sub though, doesn't it? I'm thinking u sub, but the derivative of this inside function is 2 minus 2y, and I don't have an extra factor of 2 minus 2y. So a u sub won't work. Integration by parts also does not look promising. But I remember this was part of a circle from before. I think I can complete the square on this. Now remember back in Calculus 2, we said if you have a squared term and a constant times the same variable, so like we have the y squared and the 2y, sometimes we can complete the square and then use a basic rule to integrate. So let's complete the square on that 2y minus y squared. First, I'll reorder it. I'll write my y squared term first, and then my 2y. And then remember what you have to do to complete the square. The coefficient of the squared term needs to be a positive 1. Right now it's not. It's a negative 1. So I need to factor out that negative 1 from both of these terms, from the y squared and the 2y. Negative 1 times y squared gives me the negative y squared. And negative 1 times a negative 2y would give me that positive 2y. Then, once I've done that, once I have a positive 1 as a coefficient of the y squared in parentheses, I complete the square here. To do that, I identify b, take half of b, and square it. Negative 1 squared is positive 1. I add 1 to complete the square. And then to compensate for adding 1, I subtract 1. So now I've got negative 1 times this quantity, which factors to y minus 1 squared, and and then I'm subtracting the 1. And then we have to distribute the negative to both of these terms. So we end up with a negative y minus 1 squared, and a negative times a negative is a positive 1. So inside these parentheses, we have a 1 minus the quantity y minus 1 squared. So I've got 1 minus the quantity y minus 1 squared. That's all of this, because I'm just replacing this with this. We just said that those are algebraically equivalent by completing the square. That's being raised to the 3/2. So to evaluate this, I will do a u sub, let u equal y minus 1. Then du is just 1 dy. And because this is a definite integral, I need new bounds for u. So I take my old upper bound and I substitute that here to get my new upper bound. 2 minus 1 is 1. I take my old lower bound and I substitute that here to get my new lower bound. 0 minus 1 is negative 1. So we end up with 4/3 times this integral. The 1 is still there, and this y minus 1, that's our u. So I've got 1 minus u squared. dy and du are the same thing. And then by substituting y equals 2 here, I got a new upper bound of 1. And by substituting y equals 0 here, I got a new lower bound. My new lower bound for u is negative 1. So now I need to evaluate this integral, and this requires trig substitution. So we had to complete the square, and because we have an a squared minus u squared, we're going to do a trig sub with, since the form is a squared minus u squared, u is equal to a times sine of theta. Now a squared is 1, so a is 1. And remember how trig sub works. You need to write everything up here in terms of your trig functions. So I have u equals 1 sine of theta, then 1 minus u squared, that's that expression in the brackets, is 1 minus sine squared theta, because I'm replacing that sine, or that u with sine of theta. But 1 minus sine squared is cosine squared because of our Pythagorean identities. So we're going to replace all of that in brackets by cosine squared. And if u is sine of theta, du is derivative of sine of theta, that's cosine of theta d theta. I actually think what I'll do is I'll evaluate the indefinite integral, and then we'll substitute the bounds at the end. Should we do that? Yeah, I think I would prefer to do that. So I'm going to evaluate this to get the antiderivative, and then I'll substitute negative 1 and 1 for u, and that will allow us to find the final volume. Okay, so we still have the 4/3. The 1 minus u squared simplified to cosine squared, so I'm replacing this with cosine squared. And don't forget that's being raised to the 3/2 power. And then du is replaced by cosine of theta d theta. Now remember how this works. Multiply the exponents. So that's like x to the n times x to the, or raised to the m is x to the n times m. So you have cosine squared to the 3/2. 2 times the 3/2 is going to give us a cosine cubed. And cosine cubed times cosine is cosine to the 4th. Or I could call that cosine squared times cosine squared. Now the reason I did that is because we have a rule for our trig integration. If our sine or cosine is raised to an even power, they recommend that we use power reducing formulas for each cosine squared. Now cosine squared turns out to be 1/2 of 1 plus cosine of double the angle. So each cosine squared will get replaced with that. Now multiplication is commutative, so you can take this 1/2 and 1/2, multiply those together, that's a 1/4, and multiply it by the 4/3, and so you'll get a 1/3 out front. And we still have a 1 plus cosine of 2 theta times itself. If I FOIL, I get 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. And that requires a power reducing formula as well. I've got a rule for that and a rule for that, but not this one. So I have 1/2 of 1 plus cosine of double the angle. My angle was 2 theta, now it's going to be 4 theta. Distribute the 1/2. 1/2 times 1 is 1/2. 1/2 times that cosine just ends up over here. Now we're finally ready to anti-differentiate. 1 plus 1/2 is, I'll just call that 1.5. Okay, anti-differentiate with respect to theta. So you get 1.5 times theta, bring the 2 down, the antiderivative of cosine of 2 theta is sine of 2 theta. Since there's a 2 there, you have to divide by it. We've got a 1/2 here. The antiderivative of cosine of 4 theta is sine of 4 theta. So you have a constant inside, you have to divide by it. We do all of that plus c. Oh my goodness. Now, remember our original integral was 4/3 of the integral from -1 to 1 of 1 minus, oh gosh, we've got to back substitute. I think we're going to run out of time. My video recording software only allows me to make videos up to an hour, which is why I started rushing at the end here. So this ended up being all of this, but we have to, so I've got 1/3, and that is 3/2 theta plus sine of 2 theta plus 1/8 sine of 4 theta plus c. And I guess we have to back substitute. From our trig substitution, theta is the arcsine of u. And so then I'll have 1/3 sine of theta, and sine of theta is u. Oops, that should be sine of 2 theta. Sine of 2 theta is 2 sine of theta cosine of theta. U is sine, and cosine is actually the square root of 1 minus u squared. And I think I'm gonna run out of time. Oh dear. Yes, I'm going to run out of time. There's only 1 minute left in the video. Okay, so eventually you finish this. And it would take me a little while just to do the calculations. I was trying to rush, I was trying to get it done. But let's focus on the big picture. What was it that we were doing again? All right. So we wanted to find the volume between this elliptic paraboloid and this plane. The way we do it is we graph the two surfaces, we identify the top function and bottom function. You find the boundary of the region R by setting the z's equal to each other and then sketching R. And that allows you to set up an integral. And we did that, and we got here. Then you evaluate that integral using known methods from previous classes. Unfortunately, I've run out of time and I can't show you what the answer is, but I'll put the answer in the description.